The Music of Atoms Part 2. And in this video we're going to answer the question, why is the electron buzzing around a hydrogen atom? Why is it only allowed to have certain amounts of energy? Now, in the lower six, hopefully you remember doing transverse standing waves, as in standing waves on a string. And you should remember that these only occur at certain frequencies. They only occur at certain wavelengths. For the first harmonic, the length of the string is one loop, which is half a wavelength. For the second harmonic, it's two loops, which is a wavelength. For the third harmonic, it's three loops, etc. Now, that's waves, but what about electrons? Now, hopefully, from your first year quantum physics, you also remember that electrons often behave like waves, wave-particle duality. Now, could it possibly be that the electrons in a hydrogen atom are behaving like standing waves? Maybe they can only have certain wavelengths. And if they can only have certain wavelengths, then they can only have certain frequencies, and they can only have certain energies. And that is the answer. Okay, we're going to explore this further by doing a calculation now. What we're going to do is calculate the total energy of an electron, and we're going to get an expression for that in terms of its radius in the hydrogen atom. So, total energy equals EPE plus KE, electrical potential energy plus kinetic energy. Electrical potential energy, if you've seen my video on non-uniform electric fields, you will know immediately that that's minus KE squared over R, where K is 1 over 4 pi epsilon naught, 9 times 10 to the 9. E, thanks to Millikan, is 1.6 times 10 to the minus 19 coulombs. So K minus KE squared over R. So that's okay. We know the value of all the constants. The kinetic energy is a little bit trickier. I mean, kinetic energy is a half mv squared. We know the mass of the electron, but we don't know its velocity. Is there any way we can get an expression for the kinetic energy? And we can if we use this again from the lower six, lambda equals h over mv, or h over p, which is the de Broglie equation. Lambda is our wavelength, the wavelength of the electron. So that's the wavelength in terms of the momentum. We could use this equation to get an expression for the momentum in terms of its wavelength. And we do that, we get, first of all, get the velocity equals, then get the momentum equals, multiply them together, and that's mv squared, and then divide by 2, and you've got a half mv squared. And so the kinetic energy is h squared over 2m lambda squared. Now, what would lambda be? So my electron is a standing wave. It's the minimum energy, so the smallest amount of energy, if you like, my first harmonic. What would lambda be? And thanks to Niels Bohr imagined that the electron is a standing wave surrounding the atom. And for the ground state, in his calculation, he said that the wavelength is equal to the circumference. And I can imagine that. I can imagine a three-dimensional standing wave, and its wavelength is the circumference. It surrounds the atom. Substitute in the equation above, and we've got the kinetic energy in terms of the wavelength, h squared over 8 pi squared mr squared. Let's go back to our expression for the total energy, and now we have the total energy in terms of the radius. And what I'd like to know is at what value of R is that expression a minimum? If you're a good A-level mathematician, you'll have done maxima and minima. You'll know that if we differentiate that and put it equal to 0, that will tell us the minimum energy in terms of the radius. Or, well, at what value of R is this expression a minimum? This would correspond to the ground state. Or you could do what I've done here, which is we know the value of all the constants, so we can put it into a spreadsheet and work out the total energy for lots of different values of R. And there is a value of R where the total energy is a minimum, and that value is, drum roll, that value is 0.53 times 10 to the minus 10 meters off my spreadsheet. And that's pretty mind-blowing. Why? Because that is the actual radius of a hydrogen atom. We have calculated the radius of a hydrogen atom. Wow. Now, the higher energy levels would be your higher harmonics. You know, an excited atom, n equals 2, that would be the second harmonic. N equals 3 would be the third harmonic, etc. Questions come up on this quite regularly. Often it's called an electron in a box. Because the electron can only have a certain wavelength, it's confined inside the atom or in a molecule very often. It's called an electron in a box. If it is a molecule, if you get a question on a molecule, then usually the length of the molecule is a closed loop. It's half a wavelength. Okay? And very often you have to work out the energy of this electron, or maybe just its kinetic energy. And in its ground state, then we said that the length of the molecule is half a wavelength, so that would be, lambda would be 2L. And very often you do it for n equals 1 and n equals 2, and you work out the difference between them, and that's the energy needed to excite it from n equals 1 to n equals 2, or the energy emitted if it falls from n equals 2 to n equals 1.